In this talk, we'll look in close detail at two quantum architectures and see how they can be modeled and studied. What you see here is a simplified representation of the distributed quantum application stack. At the top, we have a client who runs a distributed quantum application, for example, quantum key distribution. Then we have a quantum network, which helps to deliver the resources that are requested by the application, for instance, entanglement. At the bottom, we have a quantum architecture, the actual hardware with which the network and the application must interface in order to generate these resources or to perform quantum computation. In this talk, we'll be exploring some of the interactions between the different levels of the distributed quantum architecture stack. Before we do that, I'd like to point out that distributed quantum applications are diverse in the ways in which they request and consume resources. For instance, we have quantum key distribution, where entanglement is prepared, likely at larger distances, and quickly consumed via measurement. This application may be viewed as a networking-heavy one. Another family of applications may make use of a quantum computing cluster, where entanglement is generated among several neighboring nodes, most likely at relatively short distances, and then every network node performs a fair amount of computation that involves these entangled qubits. This kind of application may be considered computation-heavy. We also have secure delegated quantum computing, or blind quantum computing, which, like quantum key distribution, will need to connect two nodes separated by a large distance, but which also involves a fair amount of computation, so this application may be considered both networking and computation-heavy. So going back to our distributed quantum application stack picture, we can try to be more explicit about the types of operations that take place and introduce some terminology. The application demands both computational as well as entanglement or networking tasks, which arrive at some request rate. The network services the networking demands by providing entanglement, which is created at some successful entanglement generation rate. The architecture services the computational demands at some rate of computation. A central question that arises from this discussion is how the distributed quantum architecture design will affect the overall application performance. Note that the answer to this question likely also depends on the application type, computation-heavy or networking-heavy. For example, an architecture may be very good at computation, but this may not matter so much for an application that is only entanglement-heavy. We'll try to provide some answers to this question in this talk. Let's examine a quantum architecture in more detail. Any distributed quantum architecture must have some key features. For one, it must be able to perform local quantum computation. So it will have a computing component, and computational requests from a user or an application are forwarded to this component. Another key feature of a distributed quantum architecture is to be able to generate entanglement with remote nodes. So it will have a networking component, and entanglement requests from a user or application are handled by this component. And finally, a useful ability for such an architecture is to be able to perform state transfer as requested by the application. Such requests may require the cooperation of both the computing and the networking components. One possible realization of this quantum processor is with the nitrogen vacancy center in Diamond platform. The NV center has an electron which can be used to communicate with the outside world, so the electronic spin is called the communication qubit. Surrounding the center are multiple carbon atoms, which we can use for storage and computation. With a single NV, both computation as well as entanglement generation are handled by the same device, but we do have a physical division in the sense that we only use the communication qubit for entanglement generation. Meanwhile, the carbon-13 spins can be viewed as computing components. Throughout this talk, I'll be referring to this architecture as the single device design, or SD design, and this design is how present-day distributed quantum architectures are currently being implemented. Another possible architectural model may consist of two separate devices. We now have a networking device, which is used solely for remote entanglement generation, and we have a computing device, which only performs computation. Similar to the previous architecture, state transfer from one device to another requires the cooperation of both devices. But in this architecture, we have an inter-device interface for being able to move entangled qubit state from the networking device to the computing device for processing. A possible realization of such an architecture consists of two NV centers in diamond, one used only for computation and the other only for networking tasks. To transfer the state of a qubit from one NV to the other, it may be required to generate NV to NV entanglement. Throughout this talk, I'll refer to this architecture as the double device design. Quantum architectures commonly come with several physical restrictions. For instance, the NV center in diamond has a limited amount of parallelism, in the sense that we need to access the communication qubit in order to perform 2-qubit gates, entanglement generation, and even readout state. This means that with a single NV, I can't, for example, do computation if I'm currently in the middle of trying to generate entanglement. The double NV architecture partially addresses this restriction, but the state transfers in this architecture require NV to NV entanglement generation, which uses the communication qubits in both the NVs. This means that both computation and entanglement generation are halted when a state transfer is in progress. For a double device architecture, we also expect the state transfers to be more time-consuming and complex to implement than in a single device architecture. Depending on the quality of the inter-device interface, state transfers may also significantly degrade the quality of entanglement. This quantum quality, also known as fidelity, is the main focus of our work, so now is a good time to talk more about it. To give you a better understanding of fidelity, let's look at what happens to a qubit as it awaits processing in the NV. In this example, the qubit is waiting for entanglement generation to complete before it may get serviced. Since storage is not perfect, after some time, the effects of noise degrade the quality of the state stored in this qubit. As you can imagine, the quality of computation on this decoherent qubit will not be the same as it would have been had the qubit not experienced all this noise. We can use fidelity to characterize the quality of a state or computation. This is a number between 0 and 1, and the higher it is, the closer we are to the desired state or to the target implementation of a quantum gate. Entanglement is also subject to decoherence, and the longer the application waits before consuming it, the lower we can expect the entanglement fidelity to be in the end. With entanglement, there's an additional concern with quality, in that when the application transfers the state from communication to storage, fidelity decreases further because the state transfer is not a noiseless operation. So a key observation is that in systems with a limited amount of parallelism, qubits are forced to wait, resulting in fidelity degradation. Whenever computation is done after storage, we will be concerned with a quantum performance measure of gate fidelity, and whenever an entangled qubit is processed after it's been stored for some time, we'll be concerned about the entanglement fidelity. Our goal, now stated more concretely, is to study how the gate and entanglement fidelities are affected as a function of the waiting time. Here's how we contributed towards answering these questions. First, we have derived mathematical formulas for gate and entanglement fidelities for standard quantum noise models. We've also developed a Markov chain to model both architectural designs as quasi-birth-death processes under some simplifying assumptions, namely that all requests arrive according to independent Poisson processes, that completion times are exponentially distributed for the service, and finally that local computation consumes negligible time. This latter assumption is later relaxed, and we explore the effects of more time-consuming computation via simulation. Here is a simplified representation of the model. As long as there is an outstanding entanglement request, the system will attempt to produce it. Upon success, which occurs with rate μe, the system waits until an application issues a state transfer request. These requests arrive with rate lambda m, and upon arrival, the state of the entangled qubit will be transferred to a different memory location, freeing up the communication qubit to be used in further entanglement generation attempts. The actual state transfer completes with rate μm. New entanglement and computation requests may arrive at any time, and depending on the architecture and current state of the system, may have to wait until an ongoing operation is complete. That could happen in the first and third scenarios. In the middle scenario, when the system is simply waiting for a state transfer request to arrive, the system is effectively idle, so that a newly arriving computational request can be processed immediately. To give an idea of how we actually obtain fidelity, I'll give an example using the average gate fidelity. We start by choosing an appropriate fidelity formula, which depends on the specific noise model that describes how the quality of quantum states degrades with time. We then use the Markov chain to obtain the waiting time distribution of qubits that are involved in local quantum computation. This will be specific to the architecture that we are studying. We then integrate their product, and we are able to obtain the average fidelity as a function of the memory lifetimes, T1 and T2, as well as the model parameters, such as lambda E, which represents the entanglement demand rate, and mu m, which represents how quickly the state transfers can be executed. We can do a similar procedure to obtain the entanglement fidelity. Here's what we found when it comes to the average gate fidelity. It turns out, unsurprisingly, that 2 devices are always better than 1 for gate fidelity, as long as the memory lifetimes are the same. The reason for this is that qubits involved in computational jobs don't need to wait for entanglement generation when we have device separation. On the other hand, it's possible that opting for a high-quality single-device architecture is both the more economical and practical option than opting for a double-design architecture with comparably worse memories. To show you an example, take a look at this plot. Here, the single-device architecture is implemented with memories whose lifetimes are 5 times longer than those of the double-device architecture. On the x-axis, we have the state transfer rate of the double NV architecture, with higher rates being more favorable to the gate fidelity. On the y-axis, we have the difference between the double-device and single-device average gate fidelities. The different curves that you see here correspond to different local computation rates, with infinity representing our model, where the computation consumes negligible time. And lower rates could possibly represent atomic computation sequences that shouldn't be interrupted by other operations. From this plot, we can see that as computation gets slower, the single-device architecture begins to outperform the double-device architecture. Now, we take a look at the post-move entanglement fidelity. As already mentioned, the inter-device interface in the double-device design is not very hospitable to entanglement, especially when the gates used to implement the state transfers are imperfect. For this reason, we observe that the single-device architecture actually fares better in terms of post-move entanglement fidelity, and we can see that in the plot I'm showing here. For each curve color, the solid lines represent the single-device post-move entanglement fidelity, and the dashed lines represent the double-device post-move fidelity. On the x-axis, I'm varying the moving request arrival rate, which represents how quickly the application demands the state of the entangled qubit to be transferred to a different location, of course after the entanglement has already been successfully generated. We can see that as the memory lifetimes degrade, the gap between the single and double device entanglement fidelity increases. In particular, for the yellow curve, we see a really stark contrast. One more result is the post-move entanglement fidelity as a function of the moving request rate. Each point on this heat map represents the post-move fidelity of the single-device architecture. On the x-axis, we vary the application responsiveness, in other words, how quickly, post-entanglement generation, the state of the entangled qubit is requested to be moved. As we go up along the y-axis, the memory lifetimes are elongated. The T1 and T2 values that we picked for a multiplier of 1 are values that have been experimentally realized for the NV center in diamond. What this plot is showing is how unresponsive an application can afford to be based on the available memory quality. Naturally, the worse the memories, the faster the entangled qubit should be processed. To summarize, what we found is that when the two architectures are implemented with identical memories, two devices outperform one in terms of gate fidelity. But on the other hand, when the architectures both rely on imperfect gates, specifically when the state transfers must be performed, we find that the single device architecture performs better in terms of entanglement fidelity. This leads us to conclude that the single device architecture may be more suitable for network-heavy applications, while the double device architecture is more suitable for computation-heavy applications. And finally, we also explored memory manufacturing quality trade-offs and found that it's sometimes better to invest in a single device with better memories than two devices with poorer quality memories. This concludes my talk. Thanks for listening, and don't hesitate to contact us with any questions.